A pressure volume diagram of a heat engine is shown below. And part A asks us to describe the difference between an isothermal and adiabatic compression. While isothermal compression, using the first law of thermodynamics, the change in internal energy is zero, and that's equal to the heat going out of the system plus the work done by the surroundings on the system. Whereas with adiabatic compression, delta U is equal to the work done on the system. Okay, so there's no heat going in or out of the system under adiabatic compression. And therefore the change in internal energy is not zero. But with isothermal compression, the change in internal energy is zero. So heat must be flowing out of the system because the work is done on the system to obtain a constant temperature. So really have a think about that. Now for part B, we're asked to determine if heat is absorbed or dissipated by the system along the isotherm AB. Well, because we have isothermal expansion, the volume is increasing, so that means heat must have been absorbed by the system to maintain a constant temperature from A to B. Okay, so when expansion reduces the temperature, and heat must be going into the system to keep the temperature constant. So therefore heat was absorbed along the isotherm. Now part C asks us to describe why heat cannot be converted into work fully, and using an example of a heat engine. Well, this is due to entropy or disorder in the system. So if we look at a simple combustion engine, so we have a cylinder and a piston. So what this would look like in a real car engine is something like this. And then you'd have a mixture of air and fuel, which is ignited, and the explosion pushes the piston downwards onto a mechanism that rotates a crankshaft, and it's going to rotate the tires of the car. So this is a simple schematic. You'd have more parts and more than one cylinder in a car engine. Now due to increasing entropy, you're not going to get a perfect distribution of this fuel-air mixture, so you're not going to get full combustion. And therefore, you're going to get some heat going into the system, and work is going to be done by the system to rotate those tires, and the remaining heat is going to come out as exhaust. So heat cannot be fully converted into work due to entropy or increasing disorder. Now in part D, does the system do work on the surroundings or vice versa when it goes through the entire cycle from A to B to C to D and back to A? Well, in this case, the net work is done by the system on the surroundings, because for an isothermal expansion, you're going to get heat being absorbed and work done by the system. And the temperature of AB is higher than that of temperature CD. So the area under the second isotherm is going to be smaller than the area under the isotherm AB, and the net work is equal to the area between all these curves here. So work is done by the system because QH, which is the heat coming in from the hotter reservoir, is going to be larger than the heat going out into the colder reservoir. And therefore, given that it's a cyclic process, we have delta U is equal to 0, and that's equal to Q net plus the work. And given that W is equal to minus Q net, and Q net is equal to QH minus QC, which is greater than 0. So therefore the work is negative, and the work is done by the system on the surroundings. Now if the system goes through the cycle in reverse, is there a net gain or loss of heat, and why? So in this case, if we're going in reverse, and given that AD and CB are adiabats, so there's no heat going in or out of the system along AD and CB, but heat must be flowing into the system when going along the isotherm, from the colder reservoir because we have an isothermal expansion. So because there's an isothermal expansion, the change in internal energy or temperature is 0, and that's equal to QC plus the work done by the system along the isotherm. And similarly along the other isotherm, AB, well, we're going to have heat being expelled into the hotter reservoir. And along this isotherm we also have 0 change in internal energy is equal to QH, which is the heat going out of the system, plus the work done on the system in this case, because we have isothermal compression. So therefore the net heat is equal to the heat going into the system minus the heat going out of the system. And because the heat taken from the colder reservoir is lower than the heat expelled into the hotter reservoir, then Qnet in this case is less than 0. So there's going to be a net loss of heat. And if we draw a little schematic to explain this, so suppose we have this colder reservoir and the system takes heat from this colder reservoir and expels heat into the hotter reservoir. So therefore work is done on the system because you cannot move heat from a colder body to a hotter body without any work being done on the system, according to the second law of thermodynamics. So as we can see, because the cycle goes anti-clockwise, work is done on the system and equal to the area enclosed by these curves. And I'll see you in the next video.